But I want to make sure it's going to be using the OWL. Okay, just using the meeting. Okay, you can mute yourself again.
Okay, let's just wait a few more minutes. There's a few more chairs that are coming down. So it looks like we have a full house, which is great, but there'll be a few more chairs. I don't know if we have enough for everybody. They're on their way. Okay, and there's an open seat in front. Yeah, just put them around here. Okay, well, if you can take your seats as best you can. I think there may be a few more chairs on the way, but I'd like to get started here. We're very pleased to welcome Professor Inez Fung to IGPP to present a lecture to help commemorate Walter Monk's birthday. Dr. Fung is Professor of Atmospheric Science at UC Berkeley. She was born in Hong Kong, moved with her family to the US when she was 18 years old, eventually ending up at MIT, where she received a bachelor's degree in applied mathematics in 1971, staying on to earn a doctorate degree in meteorology in 1977. After leaving MIT, she mostly worked at Lamont before moving to Berkeley in 1998. She's won many awards, including election to the National Academy of Sciences and ADU's Roger Revelle Medal. Dr. Fung is an expert on climate, the carbon cycle, and how the atmosphere interacts with the biosphere and the oceans. Like Walter Munk was, she's interested in a lot of things, and I very much look forward to hearing what she has to say today. Professor Fung.
Now I need to work the technology here. The share screens. What happened to mine? Oops. Yes. Okay. And I was float through this thing. Where is the floating? Oh, here. Am I the right place? This. Yeah. Okay. Fantastic.
All right.
Okay. We are in business. Thank you very much, Peter, for inviting me. It's a real pleasure to give the talk here. The story I'm going to talk about it's a script, it's a story, it's a script story. It's not just Walter, but many people here, some in the room as well. So I start here. Okay, now this is, okay. I don't think I need to introduce this curve. Dave Keeling, Mauna Loa Observatory, and you can see the CO2 increase in the atmosphere. So the fossil fuel, but this is due to the fossil fuel built up in the atmosphere. And you can see here the increase from the combustion of fossil fuels, the emission, this is the emission of CO2 to the atmosphere. You can see the COVID barely made a dent, the different OPEC here and financial crisis, but that only made temporary dents in the emissions. So COVID here, so then it recovered with a roaring speed, the emission. So what we're interested in, the story I'm going to tell is not the fossil fuel problem, but that the fossil fuel CO2, the emission is here. What we measure in the atmosphere, the annual increase is here in blue. So the rest of it is being taken up by the land and ocean. So what we care about today is, even though I work a lot these days on the land, I'm going to ignore the land for the time being. So we're going to talk about the atmosphere and the ocean. So you can see that the airborne fraction, which is the atmospheric increase that we deduce from the atmospheric CO2 measurements, divided by the emissions, is fairly constant over this period of measurement. Okay, so it's about 50%. To lowest order is about 50%. So this is a really interesting problem to me. Okay, where the CO2 has gone. Whether with warming, whether why this airborne fraction has remained fairly constant over this period, and whether this airborne fraction will continue to hover around 50%. So what we know today is that we can estimate the CO2 emission based on self-reported statistics to the United Nations. Each country will report the fuel usage, coal and oil and gas. And so we know the caloric value. We think we know the caloric value of the fuel combusted. And so we estimate the CO2 emission to the atmosphere. So this is fairly well known, but not perfectly known. It's self-reported. And so then here we also, from deforestation, we say land cover change, not just deforestation. Deforestation is not just no CO2, no photosynthesis to remove CO2 from the atmosphere, but the detritus on the ground is decomposed, and so that's a source of CO2 to the atmosphere. In the Northeast US, we have abandonment of agriculture, and so there is regrowth of forest, so that is a net removal of CO2 as a net sink of CO2. So this is a net exchange from what we do to the land surface. So the sources are balanced by the sinks to lowest order. So we measure the CO2 increase in the atmosphere. With the ocean, we model using tracers, tritium, C14, CFCs, and other tracers in the ocean. We have some first order clue about how the ocean circulation works. And then as a residual, we calculate what the land has to take up. So for now, many decades, I feel like ever since we proposed that the mid-latitude land could be a sink for CO2, it's like running a Christmas play in primary school that every parent says my child has to be the star. So there are many mechanisms proposed for the terrestrial carbon sink. There's CO2 fertilization, there's change in vegetation, etc., but we haven't pinned that down yet. So it's estimated. So the ocean now we have measurements, and so this is from Nikki Gruber. So from the synthesis of a lot of observations. So you can see the penetration of anthropogenic CO2 in the Pacific from south to north here. In the Atlantic, south, the Antarctica is here. So you can see the deep water formation, the upwelling, the gyres, and in the Indian Ocean. So we have evidence not just of the ocean uptake, the anthropogenic carbon in the ocean, but we also have measurement of the change in pH. The color, so this is the transect. If I go from here and from the Arctic down the Atlantic and then around back to the Pacific, so here the Arctic coming south and then going north, you can see the color is the change in the pH. So it's not just the ocean taking up the anthropogenic carbon, but we can see the acidification of the ocean very clearly in the observations. So if I look at temperature, which is what we care about, is that, you know, this is another familiar graph to everyone since the pre-industrial days. The temperature has increased by about 1, depends on your reference, but about 1 degree Celsius. When I teach freshman class, I ask how many when the warmest 20 years in this entire record, in the over 200-year record, the warmest 20 years are in their lifetimes in the freshman class. Okay, so you can see the warmest years here. So this, you're familiar with this curve, we've seen it many times. And so the warming is not just in the atmosphere, but also in the ocean. This is the upper 700 from the heat content change in the upper 700 meters. And if we look at the change in the upper 2000 meters is here. So we can see heat being input. So it is not just El Nino, it's a redistribution of heat, and this redistribution of water vapor, there's heat going into the atmosphere and into the ocean. And obviously here, I don't need to introduce Argo to Scripps. So from Argo, we can see this is relative to the Argo period, the penetration of heat. Okay, we just saw the anthropogenic carbon going into the ocean. Here is the penetration of heat into the ocean from the Argo data. And so you can see the warming in the upper, in the mixed layer, and then penetrating down to the thermocline this is to 1800 meters. So when we tally everything up, the ocean takes up 93% of the heat that we have put in from the CO2. So this is a model. This is IPCC model comparison. So here is the carbon penetration, zonally averaged from many models. So this is the multi-model mean. So you can see the upwelling and the subdrop, the gyres, the gyre circulation, and similarly for the heat, but it's a different pattern from the carbon. This is from the model. I emphasized previously, I showed you from the compilation from the observations. This is from the models. We don't trust. I work with models. I don't trust models. Okay, but the problem here, the problem I want to talk about is the interaction. You know, it's fine to say there's the CO2, they go correlate. You know, they go up together, and the lawyers tell me, you cannot, the lawyers have long sentences, and the lawyer says you have a period between the separate thoughts. Okay, so now it's trying to say we can calculate the radiative forcing from all the greenhouse gases. I think many of you have done this. Okay, so CO2 at certain wavelengths can be excited into higher vibrational states. Okay, and so then that energy, instead of going out to space, goes into the CO2 and then in the atmosphere, bumps into the nitrogen and the oxygen, transfers that energy. And so this is the absorption, this is the exit. So this is greenhouse gas, the CO2 increase has contributed in radiative forcing about close to 2 watts, but okay, so watts per meter squared. When we use the word forcing, it is relative to the pre-industrial. It's due to the increase in CO2 since the pre-industrial. Okay, so increase in change in atmospheric composition. So other well-mixed greenhouse gases, methane, nitrous oxide, and CFCs, okay, so they contribute about half of that. And so they're ozone, but the aerosol reflects sunlight, and so they contribute to cooling. And I want to emphasize here that over the period when we've seen tremendous warming, the sun has not warmed up. I mean, the sun's output has not increased during the period when we've seen warming. See, the sun is not a contributor to the warming. So we have the total anthropogenic forcing is positive. That means that we are adding heat to the system. And so this is the effective warming, summing up all the greenhouse gases. We have put up 3.2 watts per meter squared additional energy into the system. And the aerosols reflect, you can see the uncertainty in the aerosols. Aerosols are short-lived. It's tough to get a long-term measurement, long-term effect on them. So it's -9 watts per meter squared. So the net is somewhere, but it's still positive. Okay, I want you to remember this number. Okay, so whether you remember 3.2 watts per meter squared or 2.1 or 2.2 watts per meter squared. Okay, that's the forcing we have experienced since the pre-industrial period. Okay, so there's more energy into the system. So when we have warming, several things happen. Okay, warmer. So there's warmer ocean. We have more evaporation. That increases the atmosphere. The increase is about 7% per Kelvin. Okay, so, and water vapor is a much more potent greenhouse gas, much more energetic, many more vibrational states than CO2. So that enhances the additional warming, so that enhances the greenhouse effect. And so we have obviously decrease in the snow, melt this ice and snow and ice. So we have a bright surface reflecting sunlight to a dark surface that reflects less sunlight or absorbs and change to absorption. So that also amplifies the system. And so the cloud cover is a challenge to all of us. Okay, if I say, make me a cloud, give you so many grams of water vapor, make me of liquid water. I'm from the tropics, I like tall clouds. Okay, so then tall clouds radiate to space at a colder temperature. Okay, so it is a warming effect because they less energy to space. Or I'm from now living in California, so there's maritime stratus, okay, broad, low clouds that reflect sunlight. Okay, so clouds is always the big uncertainty, but here at the end of the day, there could be, but not likely, okay, that the cloud cover could reduce some of the warming from the water vapor and from the snow albedo. So this is always the point where, you know, we live on the only planet we know of that has all three phases of water, okay, so far. Okay, so here is the dial in the climate system is in the water, as in the changes in the phase of the water from liquid, from evaporation to water vapor, and that enhances the greenhouse effect and contributes to the warming. So I think all of you have seen all of this in classes. I think from the ice core, you guys know about the ice core data. So from the ice core data, we get close to 1 million years of CO2, okay, in the air bubbles, CO2 and methane in the air bubbles. And then from the ice core, we can look at the deuterium in the ice, we melt the ice and then look at the deuterium and figure out the temperature. So from the ice core data, Jim Hansen has estimated, I'm sorry you can't see that, it's about 0.75 Kelvin per watt per meter squared. Okay, 0.75 Kelvin per watt per meter squared. Okay, that's when we had a lot of ice. Now I ask you to remember a number. Okay, if it's just CO2 without the water, without the aerosol, the input is 3.2 watts per meter squared. 3.2. Okay, you multiply 3.2 by 0.75. What do you get? Okay, bigger than 2. Okay, bigger than 2. So when we look at IPCC and say we want to go to 1.5, our target is 1.5, our target is 2 degrees. Sorry, okay, Equilibrium says what we know about the equilibrium, we're past that. Okay, we're past the IPCC target. So I want to do a little experiment. So what am I talking? So the question is, if we have the luxury of time, okay, which we don't have, just to do several thought experiments to set things up, something that we know that if I add CO2 to the atmosphere, a pulse of CO2 here, I added 10 petagram carbon to the atmosphere, and the ocean will take it up. There's the partial, it increases the partial pressure of CO2 across the air-sea surface, and so there will be CO2 going into the ocean. And so this using a classic box diffusion model, so you can see that the time scale, the CO2 will remain, it takes a long time to decrease the CO2 in the atmosphere. The CO2 will remain in the, about 20% will remain in the atmosphere. Okay, so the other point to make with this figure is that now I just showed you after COVID, we are releasing fossil fuel CO2 at a phenomenal rate, okay? The faster we emit this, okay, the ocean, a lot more, what we see in the atmosphere is the new carbon, okay, and the old carbon slowly getting into the ocean. Okay, so it's a time scale of the release. And if we wait forever, so we can figure out the fossil fuel uptake by the ocean, I'm looking at Ray Weiss here, so we can do the calculation, the Ravel factor, the buffer factor for CO2, that for the atmosphere, pardon me, correct me, Ray, that the CO2, so the dissolved inorganic carbon in the ocean, we have the CO2, aqueous CO2, the bicarbonate ion and carbonate ion, and the CO2 is only 1% or so of the total dissolved inorganic carbon. Lucky for us that that's what the atmosphere sees. The partial gradient of CO2 between the atmosphere and the ocean is only seeing the invasion of CO2 to the ocean sees only the CO2 and not the bicarbonate and not the carbonate ions. So the Ravel factor, the buffer factor, says that the fraction, if we increase the total dissolved carbon in the ocean by 1%, then the CO2, the partial pressure will increase by 10%. Okay, so, but the fraction you have to take into account, but basically the pushback, the CO2 pushing back, the pushback is much less than what we put in. Okay, so then you can just do the calculation at equilibrium, at the final, if we have the luxury of time at equilibrium, then the fraction, if I think of the ocean alone, then the airborne fraction is of order 0.2. It could be, depending on what you assume to be the ocean, how much carbon is in the ocean, that would change the calculation a little bit. But for our purpose, it's about 0.2, okay? That means that even when we wait forever, there will be the fossil fuel that we put into the atmosphere, there will be 20% left in the atmosphere. So if we don't do anything, if we stop everything, there will be CO2, additional fossil fuel CO2. There's no way to get back to 280 ppm to pre-industrial condition, unless we do something. And so if I now look at temperature, so this is another experiment, and many of you know this. So if I just do a stepwise increase, CO2 just go from 300 to 600 parts per million, okay? I know that the 600, so I know my point, I know the forcing, and I know the 0.75 Kelvin per watt per meter squared. Okay, so then I can figure that if I wait forever, this would be, I would get 4 degrees, okay, warming, if I wait long enough. But because the ocean slowly, the heat penetrates slowly into the ocean, this is what we have, okay? This is in a very simple calculation that would be the mixed layer temperature. The green line would be the mixed layer temperature over 200 years. So you can see here what we call warming in the pipeline. What we see is because of our water vapor, right? So the CO2 the CO2 heats the surface, and then even it has a body, right? CO2 doesn't, the water vapor will amplify. Then we evaporate more water. The water vapor is another forcing, and so et cetera, et cetera. So we loop this way. So what we have here is what we call the equilibrium climate sensitivity of about 4 degrees. And so you see the mixed layer the e-folding time for the mixed layer temperature, it's not just what you would expect using the ROSI, the mixed layer depth and the heat capacity of the mixed layer, but because of the feedback. Okay, so if you just use the heat capacity, nothing else going on, don't care about evaporation, then the heat will be lost at some time scale of 3 to 5 years. But because of this additional evaporation and additional heating, the time scale is much longer. It's about 20 years. And here it takes about 75 years to reach 67% of the equilibrium. So it's a slow process, okay? So first is if I put CO2 into the atmosphere, it takes hundreds of order 100 years for the CO2 to decrease. The second is if I put heat into the atmosphere, there is the water vapor, the whole cycle, and all of that takes time to reach equilibrium. So now, what if we stop emission? Okay, anyone want to guess? Will temperature remain flat, or will it go up, or will it go down? Yes?
Go down.
It will go down. Up. Okay, you are representing all the big models. Okay, so basically Susan Solomon had this paper that said that it is irreversible climate change. And so in all the calculations, I look at the middle panel. So here's the CO2. They did many experiments. Stop emission at 400, stop emission at 550, at PP 550, or up to here. Okay, stop emission. You can see the CO2 decrease as I showed you when I did 10 petagram. But here, you can see the global temperature sort of flat. Okay, so this is the ZEC is the zero emission commitment, which is the final equilibrium, which is over here, okay, minus the time when you stop emission, okay? And their model says approximately zero, but then because of Susan's paper, then there is now what the climate modelers love is MIPS, okay, model into comparison project, and everyone, you have a model, you run the same thing, okay? So now the MIP, so the ZEC MIP, okay, in the comparison project, we can go from negative to positive, okay? We encompass the entire suite of results. So what is happening here? So I did this calculation using a very simple model. I apologize to people who do fancier stuff, but this is a very simple model to set up the thinking. So here's the emission. Okay, so then we stop the emission and hold it to zero. The emission goes to zero. So the total inventory, the fossil fuel, I'm sorry, can I remove myself here? Oh, I can remove myself. So you can see the fossil fuel inventory stays flat. The atmosphere, like what we said, what we've seen before, increases to the point of stopping emission, and then it decreases, the CO2 decreases. The mixed layer, having a very small mass, increases a little bit, stays flat, and most of it has gone below the mixed layer into the thermocline. And then if I calculate the fractions, then the red line is the airborne fraction. We get the airborne fraction about 0.5, and this is close to what we observed, but this is without the land doing anything. Okay, so I expect it to be, there's no land sink here. So then it decreases to about 0.2, as we would expect just from the Ravel factor. Okay, and the ocean inventory. And so you see the thermocline fraction increases as a function of time, okay, after the emission. Okay, so slowly, as we would expect, the partial pressure of CO2 in the atmosphere is still higher than that of the ocean, and so there's penetration into the ocean. And so here, if I look at a slightly different calculation, that if I look at the temperature change, okay, holding the airborne fraction at final at point 2. So the red line is what I would, if the CO2 is the equilibrium at any time. Okay, if I know the CO2, I would say, given the forcing, I can calculate the forcing and say, if I multiply by 0.75, if I had time, okay, this would be the warming. Okay, so given the CO2, then this would be the warming. And so this would be the equilibrium warming, like when I did the flat 600 ppm. And so this is what is realized using a simple box diffusion model and an airborne fraction of 0.2. So you can see the warming in the pipeline. It is correct to say that there will be additional warming because at the time of stopping emission, there's still warming in the pipeline, okay? So that heat will come out, okay, sooner or later. Okay, so the water vapor will continue to evaporate and there will be warming in the pipeline. But here, as we decrease the CO2 decreases in the atmosphere, the forcing decreases. And so there's a slight, so the forcing decreases and so temperature might decrease depending on the time. And so here we get the zero commitment is the final. This is not long enough, but I'll just pretend this is the equilibrium. It isn't, but it's a positive commitment. Okay, so here in this calculation, if I stop the emission, I would increase the final equilibrium temperature would be warmer than at the time I stopped the emission. So if I have if I have a different diffusivity, then you can see we reach, the ocean can take up more of the heat. And so there is a different, there's still a positive zero. The temperature would still increase at final equilibrium versus the time that I stop, okay? But some models actually get a cooling, okay? So we're trying to figure out why would I get a warming and how do I get a cooling? So I was lucky. Graduate student walked into my office. He's not my student. He came into my office and said he wanted to work with me. This is Nathaniel, and this is Nadir. And so to ask me to work with them on this simple calculation. And I just want to point out that they have a project called Climate Up Close, where they have they and their friends, several of them, go to small towns. They've gone to Florida small towns and to Pennsylvania small towns and talk to whoever could invite them to fairs, to churches, to synagogues, to other places to talk about climate. Okay, so this is a self-organized, they just go on their own and they try to get, anyway, so that's a digression. So anyway, so they came in to my office and they wanted to understand, what controls the zero emission commitment. Okay, what the temperature increase might be if we stopped emission. So they came up with a very simple model. Okay, we're not talking about, I talked about time scale. We're not talking about time scale. We just say, here is the time when we stopped emission and then we wait forever. And so look at the final equilibrium. So you can see there's two modes, as I said when I talked about the CO2 decrease, there's the fast mode related to the mixed layer and then a slower mode related to the thermocline. So here, if we have just look at the temperature in the surface layer, then you have the forcing, and then this is the cooling to space with all the feedback, the water vapor, the clouds, and everything feedback in here. And then there's an exchange, just a very simple exchange with the deep ocean. Okay, so at equilibrium, depending on how your time scale, then the ocean has reached equilibrium. It is no longer changing. Okay, so the flux out of the mixed layer is gone. Okay, so the equilibrium is maintained by the forcing versus the radiation to space. And so the final temperature would be between the feedback, so this is the fast response, okay, and versus and the slow response, okay, somewhere in the middle. So this is the crux of it. This is all the physics. I apologize if I left out some of your physics, but this is the simplest way to think about this problem, is that there's a fast mode and a slow mode in the ocean. And how do we think about this? So you can crack through, I won't go through the algebra here, that you can write the temperature change at final is proportional to the cumulative emission versus the pre-industrial, how much the CO2 has increased in the atmosphere. And then this thing, which is the airborne fraction at the final, in my case, I was hoping it would be 0.2, okay, the ocean taking up most of the Ravel factor in the ocean taking up a lot of the CO2 that we have emitted. So the equilibrium climate sensitivity is what we would expect, okay, at the end, when if we just double CO2, what we would expect. And then the airborne fraction when I stop emission, and then the rapid, so the transient climate response from the models is calculated if everyone increase your CO2 at 1% per year until it is doubling, okay, which is in 70 years. So what is the temperature change in 70 years if you increase CO2 at 1%? So that's the fast response. So the question here we have is between the long term captured by the equilibrium and the short term, the fast response captured by the transient, the TCR, the transient climate response, okay? So you can play with the algebraic limits. So at the end of the day, the ratio of your final warming, okay, over the warming at the time when you stop is given by the ratio. The numerator is AF over AZE, which is how far AF is the final equilibrium, 0.2. Okay, and when I stop the emission, if it is now, it will be 0.5. Okay, it is about half. Remember, the airborne fraction now is about half. Okay, and if we wait forever, it would be 0.2. Okay, so this is a measure of the carbon disequilibrium at the time of emission, at the time when we stop emission. Okay, the denominator TCR over ECS is a measure of the thermal disequilibrium at the time when we stop emission. Okay, so if I have only the fast response, okay, if the fast response dominates, then at the time when I double CO2, I have taken up all the heat I need. Okay, so the deep ocean, the diffusive ocean is not in play. Okay, because everything in the final equilibrium. Okay, because all the heat that's there is taken up. But so that would be if this is large. But if this is small, that means that at the time of stopping emission, there's a lot of heat in the pipeline, okay? So it's going to go slowly into the system and warm up. Okay, so so you can look at this and see that is zero if the carbon disequilibrium is of the same order as the thermal disequilibrium. And if at the final equilibrium it is a warming, then it is because the numerator is greater than the denominator, so the carbon disequilibrium is bigger than the thermal disequilibrium, and similarly for the negative. Okay, you can see very simple. It's very simple. It's how fast the ocean is taking up the carbon versus how fast the ocean is taking up the heat. Taking up the carbon in a way without biology, I apologize, no biology. I used to say box model is biology is an optional extra. Anyway, so without biology, I think I know from the chemistry, from the Ravel factor, even the Ravel changes, okay, and from the tracer distributions, that I have a better hold, I have better understanding of the carbon disequilibrium than of the thermal disequilibrium, because the thermal disequilibrium is related to the clouds in the atmosphere, what the feedback is, deep water formation and isopycnal diffusion and coastal up, etc. Lots of processes in the thermal part of the problem. So if we look at the model, then you can see here, this is the many climate models that have participated in this MIP, in this model intercomparison experiment. And you can see the ratio is some models give me cooling at the final, some models give me warming. Some model, the one that Susan used, the one that I showed you in the paper, is in the middle. That has very little warming. Okay, so you can see the whole range, but you can see the whole range in terms of given that we know we have a little bit firmer control, not no, on the carbon disequilibrium, then this is the thermal disequilibrium in the model that we also calculate. Okay, so you can see this very simple conceptual model can explain how fast the heat is being taken up versus how fast the carbon is taken up. So you can plot this. This would be a measure, again, of the thermal disequilibrium. So if it is large, that means that at the time of the cessations emission, we have reached close to the final temperature. Okay, whereas here we are very far from the final temperature. So you can see here and the airborne fraction, this is what we are expecting in the present day. So Susan, looking at the model, this is about half, and that's about half. Okay, so the final temperature is okay, is close to is the same as there's no additional warming. Okay, because that model they chose is a good model that did that. But you can see here that if the final airborne fraction is positive, okay, that there is a high likelihood of warming however fast. So the carbon part, okay, the carbon part is if the final airborne fraction is positive, okay, then that whatever the thermal disequilibrium is highly likely that we will get a warming. Okay, so it's very straightforward here. So the outlook for us is that, another round of MIP. Okay, so we started at I'm going to say last century. We started putting interactive carbon cycle into the global climate models. And so then we prescribed the fossil fuel emission, and then we let the land, the photosynthesis and the decomposition do their thing. We let the ocean chemistry and the biology and the mixing, and then the residual, the airborne fraction will be the one that is radiatively active. Okay, so we had many models participating in that particular MIP. So now it's IPCC standard exercise, and the climate models are now called Earth system models with all the interactive biogeochemistry. And so here, with what we learned from the models, and I emphasize this is from the models, from many models that have participated. In the first round, I said it was BYOM, bring your own model. Okay, so we didn't specify the resolution or anything. So anyway, so the expectation is that from the models is that increased stratification in the ocean, there would be slower mixing. And so then there would be a larger airborne fraction. And then also, the land ecosystem, this is always the competition between greater photosynthesis, more warming, high latitudes, okay, more nutrients with the permafrost, or and decomposition, faster decomposition because of the warmer temperature. And then there are wrinkles about what happens to all the permafrost carbon when the permafrost melts, okay, etc. So the expectation is that both the ocean, when we let the ocean carbon system interact with the climate, and when we let the terrestrial carbon system interact with the climate, with the warming, then the warming feeds the warming, it amplifies the warming. So both are both, as far as we know, is amplify the forcing, and so we expect the airborne fraction to increase from just expectation from the models. So here we have this, and so the outlook for us is that we are looking at a lot more warming in our future, even if somehow by magic we stop emission. Okay, so there are calculations I won't show you of if we have a slow rise, a Gaussian type emission, instead of going up and then just zero out everything, a slow decrease, it just shifts the time. Okay, it doesn't change all of this. But the very simple analysis that I have shown you, the carbon disequilibrium and the thermal disequilibrium depends on the ocean, depends on the ocean circulation, and depends on how perturbations are mixed. With the ocean thermal perturbation, there's a possibility of changing the ocean circulation, okay, changing density, changing circulation. And with the carbon, there isn't much, but there's a possibility of changing the biology, which we know very little about. As we know, we're struggling with the terrestrial biology. So it brings me to Walter. His papers, Abyssal Recipes, and Abyssal Recipes 2, all focused on how you maintain the vertical structure of temperature in the ocean. He looked at C14, he looked at oxygen, there's the downwelling, and how do you, there's the deep water formation, upwelling, and how do you balance, how do you maintain that structure? And then what are the mechanisms with Carl Wunsch, what are the mechanisms for that diffusion? So the early paper was 10 to the minus 4, and the later paper, he estimates from the tracers is 10 to the minus. So there's a whole range. So this is where I am now. I still think of Walter. I see the twinkle in his eye. I see the smile on his face. And now I also see Walter, what processes determine the vertical heat transport in the abyssal ocean. So I'll stop here. Thank you very much.
Thank you. Are there questions?
Yes.
Oh, hi. Yay. There's also a dynamical thing going on.
Yes,
is the
of course.
winds. And the winds are strengthening,
Yes.
especially in the southern hemisphere.
Yes.
So this is somewhat counterbalancing the increased stratification.
Yeah.
And it's keeping the ventilation probably going.
Yeah.
And as tropical storms increase,
Yeah.
we'll get more.
Yeah.
So there's maybe a tiny dip downward,
Yeah.
but in that.
Yeah. So this is where, I worked with the first generation of coupled carbon climate models, and now following the second and the third and other generations. When I look at the models, I've worked with models for a long time, and the models is the best representation of what we understand about the circulation, about the carbon cycle. And the divergence of results, is also telling me that we need to tighten up. There are many more things to think about. The feedbacks of wind, the changing in the wind, and there's more evaporation or less evaporation, etc. So I'm looking at Shangpeng, and the feedbacks from the wind is not something So what I have presented here is really a much more conceptual picture of how do I think about the equilibrium, final equilibrium, bringing the carbon disequilibrium together with the thermal disequilibrium to come up with a simple way to start parsing out the model results, okay, which is a lot of color figures and stuff, and it's tough for me to make sense of. So I'm really grateful to the students. And one of the pleasures for me has always been students coming in and teaching me new things, taking me in new directions. And I really am grateful for those, for Nathaniel walking into my office and say, I want you to work on this with me. He's not even my student. So anyway, I'm really grateful to the students. Yes.
I may have just missed this, but what did you choose to do with the land carbon sink? Did you keep it at a constant fraction?
No, so here, I just waved my arms about this. Oops, I just waved my arms about the land carbon sink because it was too messy to include here in the simple. So all I'm saying is that, you know, when I did the contemporary period, my airborne fraction was like 0.6 or higher than the 0.5, okay, because I didn't include the land in the simple conceptual picture. And here, when I talk about the future, I don't know how the land, how the competition will change. I don't know how the vegetation distribution, different species would be in different places, and they would do different things, and etc. So the land to me could change it to positive or negative, okay. But from what we know, what we think we know from the coupled models, the land, when we have warming, then the net is more CO2 to the atmosphere, even with changing vegetation. But that's really based on, you know, you should look at the land model and say, this is what we understand at this time. When I talk to ecologists, I get very scared. It's adaptation this adaptation of different tree species to different climates, and etc. So the land is an unknown in this. I deliberately not talk about the land here.
So you assume that it's zero?
No, I'm saying that here, that the land will probably push it to here. Okay, the airborne fraction, you know, at equilibrium now, okay? This is at equilibrium, not now, okay? At equilibrium. Okay, if I just do the Ravel factor and all that, I get 0.2. The final airborne fraction would be 0.2. But if I put in the land, if the land turns out to be a net source of CO2 to the atmosphere, then the airborne fraction as defined would be higher than 0.2. Okay, so I didn't want to go into, because it's just into how the land works, the land models work, because it's just a mess. Okay, so it's a very free for imagination at the moment. Yes?
Can we, building on that point, can we get an observation of the strength from the volcanic eruption that seems to induce?
Yeah, so the models, the climate models have been tested, you know, from Agong, from Stamos old book on Krakatoa, the cooling. So that's been tested very well, because now we have satellite observations of the aerosol loading. So we know the reflectivity, and so the cooling following a volcanic eruption would be at most 2 to 3 years. Okay, because the aerosols would go away.
I meant the airborne fraction. You showed the airborne fraction.
Yes. So ask your question again. Sorry,
Yeah. So the airborne fraction dipped in your third slide or so.
Yes.
It dipped pretty significantly from 0.5.
Yeah.
Can we get an observational?
Yeah. So there we know El Nino. I sort of glossed over that. So there are lines. So El Ninos, you know, so Brazil would be dry, the Amazon would be dry, and so there's less photosynthesis, okay, etc. We can tag the interannual fluctuations to what the terrestrial carbon cycle is. Okay, so basically, yes, it's been tested many times. And that now we have the satellite observations of the NDVI of the photosynthesis, and now with new satellite observations of the solar-induced fluorescence, which is a proxy for gross primary productivity, so we can do the photosynthesis part. What we cannot do is the decomposition part. Okay, we don't have the soil. We don't know how much carbon is in the soil. In the first calculation, in the first couple carbon climate calculation, Peter Cox, the Hadley Center model, went berserk. Okay, basically the model went dry, and he had one large bucket of carbon, soil carbon. It's like you have the entire ocean. You don't have a mixer, you don't have a ventilator, thermocline. You just have 4 kilometers of ocean. So then anything happens, that the entire ocean. So he had he killed the trees, and then the decomposition, there's a litter, and the decomposition took over. So his CO2 increase was tremendous. Okay, so we've done a lot of tests here that I have not had time to talk about. Okay. You had a question? Somebody. Okay. Yeah, right.
I don't know if I want to ask this, but you pointed out early on in your slides that about 60% of carbon's radiated forcing is caused by other gases that are anthropogenic.
Yes.
Among them are very short-lived gases like methane, and very long-lived gases like nitrous oxide and some of the CFCs. So do you want to hazard a guess about the impact of, 60% is a pretty big number. So do you want to hazard a question about guess about the impact of these things going forward in time?
I'm looking at you, so depends on whether, no, I think Susan Solomon made a very important point, that with the Montreal Protocol, with the decrease, at least the projected decrease in CFC 11 and 12, the radiative, they're much more potent greenhouse gases, 10,000 times more than molecule for molecules, 10,000 times more effective, or more than that. And so we would have been much warmer if we didn't have the Montreal Protocol.
Sure, that's for sure. But she's also working on the modeling of what happens to the gases that are conserved in the ocean, and then when we stop emitting them, they come back.
They will come back up. Yeah, Paul Weinberg has made a big point about that coming up. And I have done a calculation. I didn't show you where the heat is coming back up. Depends on how I play with the diffusivity. The heat could come back up. Yeah. Okay. So we are in uncharted territory, and I think we are in uncharted territory, especially about processes below the thermocline in the ground.
Thank you.
Okay. Yeah.
I'm interested to ask whether you consider the change, why you don't conceptual model, whether you consider the change in the ocean simulation and how the stratification mixing changes over time as the ocean absorbs the CO2 and the heat. And if the answer is yes, then
So basically, I call them monster models, the large climate models with everything in it, has all those processes in it. Okay, so I could take those processes and parameterize the change in the diffusivity as a function of temperature or as a function of something. And I've chosen not to do that in the conceptual model. Yes, of course, it's doable. But you saw that with that ZECMIP, with all the models running, I could get it there, right? So I'm not putting in yet another point in that range. I'm trying to understand, why do we get that range? Okay, why do we get that range? Because the models, that set of models have different carbon processes, okay, and they have different cloud processes and different other processes, and then different circulation. Okay, so yes, we could easily do that. Okay, but that's why I put in words that we expect, that the stratification, there will be less mixing, but that ignores the wind processes. Okay, so they're different things. So we can play sensitivity, in my head it's just trying to understand how can we make it positive, how can we make it negative. Okay, what processes, and then to see what data or what measurements do we need. You know, I did this whole calculation in the last century. I'd like to get an A, but there's no data to show that I did very well. So this is where it's a plea for more observations, okay, and a plea for understanding. And I think that Walter's papers are very instructive to come back to. It's just I don't know. So we don't write those things anymore. I don't know. Yeah.
Well, I'm sure there could be a lot of more questions, but we're at 4 o'clock. We have a reception, which I hope you will all join us to celebrate Walter's birthday. And let's thank Inez again.
Thank you.